Radio, welcome to Lesson 7, which is the introduction to probability, which is called Compound Events in Probability. Like normal, we're going to start off with a warm-up on what we've done a bit of so far. So the first question says the sets A, B and C are subsets of U, the universal set. They are defined as follows. So U equals positive integers less than 16. So you're probably aware that that means not including 16. So if you want to, you might want to write those numbers out. It can be helpful to have them written out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. I won't read the others out because we're actually asked to do that in question A. So list the elements, if any, of the following. So as you can see, A is prime numbers, so numbers that have exactly two factors, one in itself. So of course we don't include the number 1 because 1's not a prime number because it has only one factor. So the first number in this set will be 2, then the other prime numbers are 3, 5, 7, 11, 13. So we stop at 13 because our set only goes up to numbers less than 16. So that's 2, 3, 5, 7, 11, 13. The next one to do is B, and B is factors of 36, so numbers that divide evenly into 36. So from our universal set, we've got the numbers 1, 2, 3, because 3 times 12, 4, because 4 times 9, 6, because 6 squared is 36, 9, 12. And that's all the ones that are less than 16. C, as you can see, is multiples of 4, that's easy. Multiples of 4 start with the number itself and continue upwards. So all we've got is 4, 8, 12. So only 3 numbers in that set. And this last one here, A intersects B intersects C. So basically you're looking for what elements are in all of those 3 sets, A, B and C. So if you have a careful look, like 4, 8, 12, 12 appears in both C and B, but it doesn't appear in A. Another example is 2 appears in A and B, but doesn't appear in C. So if you look carefully, you'll find that there's actually no elements that belong to all 3 sets. So you can just say null. The null set is the answer for that one, because there's nothing. Then we're asked to draw a Venn diagram showing the relationship between the universal set A, B and C, and write the elements of U, A, B and C in the appropriate places in the Venn diagram. So you know that there's no intersect between all 3 of them. So you don't have to draw 3 intersecting sets in this particular case, only in this particular case, because you'll notice that there's no elements in C that also belong to A. So there's a different way you can draw this Venn diagram. I don't think you'll get in trouble if you do show 3 intersecting sets and you just leave the intersection between A and C empty. But this is a possible way. I'll show you the 2 possible ways that you can draw it. So I have to draw it very small. I'm going to draw 2 of them on here. We've got a universal set. So I'll do it with 3 sets drawn this way. So this is the way it's probably going to be drawn in the mark scheme. A, B and C. And that's all because, as you can see looking above, there's no numbers that belong to C that are both purple and blue. C and A. So let's start to fill all of this stuff in. We know that, let's look at the intersect of A and B. We've got 2 numbers that are in the intersect of A and B. That's 2 and 3. No other numbers are in the intersect. So this is a bit hard to see because I'm drawing it so small, sorry. What numbers are in the intersect of B and C? And we've got the number 4 and we've got the number 12. So I'm going to draw them in first. Then I'll draw the remaining ones that are in A. So the remaining ones in A are 5, 7, 11, 13, the prime numbers. So what are the remaining ones in B? The remaining ones in B are 1, 6 and 9. And what are the remaining ones in C? Just the number 8. So you might mistakenly think that you're finished. Don't forget that the universal set includes all of these numbers from 1 to 15. So if you're not sure, just count through them and see which ones are left on the outside. So what you can do is you can count them like 1, 2, 3, for example, 4, 5, 6, 7, 8, 9. We don't have 10. We do have 11 and 12 and 13. And we also don't have 14 and 15. So if you were to draw them overlapping, like this, I don't not sure, I don't think you would get in trouble if you tried to draw them overlapping, but this is the best way to draw it, for sure. A, B, and C, so the first one is the best one. And then, of course, the intersect is just empty, so you don't put anything in there. You can put in the overlap of A and B, though. Overlap of A and B is 2 and 3, and the overlap of B and C is 4 and 12. And then you can fill in the other sets. So A, again, we've got 5, 7, 11, 13. B, we've got 1, 6, and 9. And C, we have 8. And don't forget the numbers on the outside still, 10, 14, and 15. So they're the two ways you can draw it, but as I said, this is the best way, the first way. It's more specific. But if you didn't see that to begin with, potentially, like, you could start with the 3 intersecting sets. And then you were just asked from the Venn diagrams, list the elements. So list the elements just means like write what numbers in this case are in there. So we've got A. What part of A intersects with B union C? What might help is, if you're not sure, just draw a little diagram and you can do the shading. So there's your A, B, and C. So which part of A intersects with B union C? So here's A. So here's B union C now. B union C is all of that. Which part intersects? It was just that little part here. So I'm going to undo that. I'm going to make sure my answer is just the shaded part here. So this is the area which is A intersect B union C. So remember, when you're doing the intersect, you shade both of them separately and then see which one part got shaded twice, and that is the answer. So the part that's in B union C is just 2 and 3. Now let's do the next one, A intersect B dash. So A intersect B, all of that in brackets dash, sorry. So you might want to do this again, kind of is helpful really. So A intersect B, we'll shade that first. A intersect B is just this little part here. So A intersect B dash will be everything outside of that. So I'm going to undo that. And we need to shade everything on the outside of the intersect there. So it takes a while to shade because there's a big area. I'm just doing it very roughly. I'm sure yours will look better, but this isn't a question anyway, so I don't need to be that specific. All they want us to do is list the elements. So if 2 and 3 are the numbers on the intersect that's not shaded, then every other number in the universal set, which is the numbers 1 to 15, are part of the set. So I've got to write all of them out. So 1, don't include 2 and 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the last one in the warm-up, A intersect B dash, which is what we just did here, which intersects with C. So what part of this green area above intersects with C? I could probably just use the diagram above. So C is over here. So if I shade C, the overlap part is that part there. So I'm going to undo that. I'll do a little diagram if it helps you, a separate one. So the part of A intersect B dash, the red area which intersects with C, is actually just C, strangely enough. So just list the elements of C, 4, 8, and 12, the multiples of 4. And finally, that's the warm-up done. Now let's move on to the actual lesson. So compound events in probability. So just recapping, you did a bit of introduction to probability in Year 8. So from Year 8, how is probability calculated? You might remember that it is the probability of event is the number of ways the event can occur over the total number of possible outcomes. So for example, when you flip a coin, there's 2 outcomes. Probability of flipping a tail is just 1 in 2. So just be aware your answers for probabilities can be written as fractions, e.g. for example 2/3, or a decimal, for example exact answers. So for example 2/3 is the same as 0.6 recurring. You could also do something like let's see, 1/10, or you might do 0.1. If you do need to round any, then you need to round them to 3 significant figures. But 1/10 is exactly 0.1, so that's an exact answer. So now let's look at this example. A dice is rolled. What's the probability of getting an even number? So first of all, think of what's going on here. The total number of possible outcomes when you roll a dice is there's 6 outcomes in total. So that becomes your denominator. So even numbers. So by an even number, we mean like 2, 4, and 6 on a dice. So what's the probability of getting an even number? It's 3 and 6. And don't forget to simplify your answers. That 3 and 6 simplifies to 1/2. A number greater than 5, there's only one option, which is 6. So it's just 1 in 6 for that. So number greater than 5 doesn't include the number 5. A number less than 7, you've got like 6 options there. So it's going to be 6 out of 6, and 6 out of 6 simplifies to the number 1, because 6 divided by 6 is 1. The square number on a dice, the square numbers are 1, because 1 squared is 1, and 4, because 2 squared is 4. So you've got a 2 in 3 chance, sorry, 2 in 6 chance, what am I saying? 2 in 6 chance, which simplifies to 1/3. You can divide the top and bottom by 2. A negative number, are there any negative numbers on a dice? No. So if you want to write it out as a fraction, it would be 0 over 6, which is just 0. So you can go straight to writing 0 if you prefer. And a real number, so remember any number is a real number, so all 6 numbers on a dice are real. So 6 divided by 6 equals 1. So notice that I'm always simplifying my probabilities. It's always good to do that. Another example, a glass jar contains 6 red, 5 green, 8 blue, and 3 yellow marbles. Just might be always worth working out the total. Total equals 6 plus 5 plus 8 plus 3, which equals 22. If a single marble is chosen at random from the jar, what is the probability of choosing a red marble? So looking up, there's 6 red marbles. So write 6 over 22 to begin with, and then simplify your answer. You can divide the top and bottom by 2. It's always good to simplify in the second step and have the unsimplified answer first. Just in case you make a mistake in simplifying, the examiner might overlook your simplifying mistake. A blue marble, there's 8 blue marbles, so that's 8 out of 22, simplifies to 4 out of 11, of course. A yellow marble or a green marble. So that means that you're including more. You're including yellow, 3 yellow, or 3 green. So in total, 3 and 5 marbles makes 8. So if you want to, you can show a bit of working out. 5 plus 3 over 22 equals 8 over 22, which also happens to equal 4 over 11. And the next one, not a red marble. So how many are not red? So if 6 are red, then the total not red must be 22 minus 6, which of course equals 16, which are not red. So write that as a probability. It will be 16 over 22, which simplifies to 8 over 11. And the last one, probability of a red marble plus the probability of not a red marble. So you worked out probability of a red marble in A, you got 3/11, plus probability of not a red marble you worked out in D, you got 8 over 11. So remember when you add fractions, if you've got a common denominator, it doesn't change, it stays 11. So when you've got a common denominator and you're adding or subtracting fractions, you just add the numerators. So 3 plus 8 is 11, and 11 divided by 11, think what that is. It's number 1. And then on the next page, you're asked to look back on that particular question, so keep that in mind when we go to the next page. From the previous example, the probability of an event happening, e.g. red, plus the probability of an event not happening, e.g. not red, equals the probability of A plus the probability of A dash. And you might have noticed from the previous examples, when you add the probability of an event happening to the probability of the complement of that event happening, they always add to 1, because probabilities in total need to add up to 1. Think of it as like 100%. 1 is like 100%. Now let's move on to the next example. A spinner has 4 equal sections. This is an example of a spinner. You spin it around and see which colour it lands on. They're equal sectors, coloured yellow, blue, green and red. After spinning the spinner, what is the probability of landing on each colour? So you can see they're equal sections, equal size sections, so you can just say each section will have an equal probability, and try to think what that probability would be. Each section would have an equal probability of, you probably guessed correctly, 1/4, because there's 4 equal sections, so a 1 in 4 chance of landing in each section. Let's look at the next example. Why is the below spinner biased? So as you can see, the area for 2 is 4 times as big as any other area that you've got going around here. So you can word that in different ways. So what will I say? I'll say you're 4 times as likely, 4 times as likely to land on a 2 than on a 1, 3, 4, or 5. So you might have said it in a different way, so long as you say something to that effect. That's what we're asking for. And then the questions follow on from this spinner. What's the probability of getting the following numbers when using the spinner? So probability of getting a 3, you can see. In total, think of 2 as kind of being the 2 section. You could split it up into, 8. I didn't split that up very well. So you can split it up into, the whole thing has got 1, 2, 3, 4, 5, 6, 7, 8 eighths in it. So you can think of it as being split up like that if you like. So the probability of getting therefore a 3 is just 1 in 8. Because it's 8 little slices of pie in total. Probability of getting a 2, so remember you can split a 2 up into 4 little 8s. So there would be 4 8s, but don't forget that that can simplify to 1/2. Probability of getting a 5 is 5, just equal to 1/8, like before. And probability of not getting a 2. So not getting a 2 is all of this section here. So as you can see, it's just a 4 in 8 chance, or you might have gone straight to saying it's 1 in 2. So I'm going to go 4 in 8, which equals 1 in 2 chance. So next we'll try an interesting kind of little real world problem just to make it all a bit more interesting for you, hopefully. So an interesting problem to solve. Imagine you have been tested in a large scale screening program for a disease known to affect 1 person in 100. So that's actually important. 1 person in 100, you might miss that when you look back at it. The test is 90% accurate, that's also very important, and you test positive. What is the probability that you do actually have the disease? So try to think, let's test how accurate this test is. Well, how reliable this test is, sorry. We know it's 90% accurate, but how reliable is it, is a positive result? So out of 1,000 people, how many would we expect to have the disease? So this is where it's important, for a disease known to affect 1 person in 100. So try to think, you might just want to write 1 person per 100. So therefore in 1,000 people, how you can show you're working out, okay, 100, because it's 1 person in 100, times 1,000 people equals 10 people in total. So out of 1,000 people, we expect only 10 people to actually have the disease, according to the question. So out of those who do have the disease, so what we just worked out then, how many would we expect to have a false negative, and how many to have a correct positive result? So there's going to be 2 answers to this. So the part that's important is up here, the fact that the test is only 90% accurate. So you might just want to remind yourself of that. Test is 90% accurate. So let's work out one of them. So let's work out the false negatives. So 10 people in total have the disease. So, test first of all. 10 people in total have the disease, but we'll deal with that afterwards. So don't forget also above here, test is 90% accurate, so therefore 10% inaccurate. I forgot to mention that, sorry. So if it's 90% accurate, the test, of course it's 10% inaccurate. So to work out how many of these 10 people might have a false negative. So turn this 10% into a fraction. So percents are out of 100, so write 10 out of 100, and then times it by our answer to the above question. So we only expect 10 out of 100 of those 10 people who do have the disease to get a false negative. So that, when you work that out, you'll get one person who we expect to get a false negative out of those 10 people above, in the above question, who do actually have the disease. And how many to get a correct positive, the second part, remember it's 90% accurate. So turn 90% into a fraction, 90 over 100, and times it by the 10 people that we found who do have the disease in the above question. And how many in total do we get with correctly identified positive results? So we get 9 people when you work that out. 9 people who are correctly identified with the positive result. So of these 10 people who do have the disease, we expect that one of them received a false negative from the test and 9 of them had a correct positive from that test. Now we're asked, how many of the 10,000 don't have the disease? So that's an easy one, because we worked it above. So we worked out that 10 people out of 1,000 have the disease. So that was important. So therefore, if out of 1,000 people, if 10 have the disease, 1,000 minus 10 equals 990 people don't have the disease. So that's a bit more straightforward, that one. Then we're asked, of this amount, so what you just worked out, 990, how many of these would receive false positive results? And how many would receive correct negative results? So remember, the test is 90% accurate. So don't forget to remind yourself, the test is 90% accurate. And 10%, therefore, inaccurate. So that's always good to remind yourself of that. So from 990, let's work out the 10% who are inaccurate first. So let's do 10 over 100, turn that 10% into a fraction, times it by 990 people who don't have the disease. So that equals 99 people. And that's the inaccurate part with a false negative result. And then it's 90% accurate, so turn 90 into a fraction and multiply it by how many people we expect don't have the disease. And you get 891 people who have a correct negative result. Correct negative result. So let's see, how many have incorrect results so far? So we have, in the above question, we worked out that one person up here with a false negative, and 99 people, let's see, sorry, up here. Did I say false negative? Yeah. Oh, sorry, this should have been false positive. That's why I'm getting confused. I see it's false positive. So one person above has a false negative, and 99 people down here have false positives, and let's continue on. How many positive test results would there have been in total? So what we need to do is add something up. So there were 99 people had false positives. So you just might want to make a note of that. That's the amount we found that have false positives. And how many have correct positives? In the second question, we worked out that there were 9 with correct positives. So just add those two together. 99 plus 9, we get 108 people. So of the sample of 1,000, 108 people would have come up with positive results for the disease, but of those, 99 would have been false positives, and only 9 of those would have been correct positives. So from above, how many out of the 1,000 really do have the disease and received a positive result? So only 9 people. So just ask me to look up and observe. Only 9 people have correct positives. That comes from here. So only 9 people have correct positives. This is just required because it helps us out with the next part to write that down and make note of it. What therefore is the reliability, the accuracy, the reliability of a positive result? So 9 people in total have correct positives out of the total number of people with positive results. Can you see above where we work that out? That was up here. So 108. So this is, again, let's just remind ourselves, these are the correct positives. Just 1 second, I'll just have to pause and start again. I'll come back, just have to pause and open it again. So there was 9, as we said, correct positives. 9 correct positives here, and this was the total positive results. So does that simplify? 9 over 108. At the top and bottom, numerator and denominator are both divisible by 9. So 9 divided by 9 is 1, 108 divided by 9 is 12. So what is the reliability of a positive result? So if you received a positive result for this particular disease test, how reliable is it? It's only 1 in 12. Would you consider that reliable? Probably not. So we'll say not very reliable. So what was the point of that? It was just to show you a little real-world application of a bit of probability. So understanding this kind of question is very important because it leads to exactly the dilemma you might face if you are screened for a major killer like cancer, tested positive. Should you immediately opt for a risky procedure to investigate further, or would that be to submit yourself to unnecessary surgery? So it's a sign that maybe you would want a second opinion or get a different kind of test from a different practitioner. Okay, let's move on to the regular stuff. So this lesson we have to learn a bit about independent and dependent events. You might not have heard of them before. So 2 events are considered to be independent if the occurrence of one of them does not affect the probability that the other occurs. So here's a classic example. If you flip a coin, so the outcome of flipping a coin, it won't affect the outcome of rolling a die. Like a die is just like meaning like a dice. Therefore, these 2 events are considered to be independent. Because they don't, the outcome of one doesn't affect the outcome of the other. Another example is the outcome of drawing a raffle ticket from a hat, and not replacing it. Sorry, this is a different kind of one for independent. So the outcome of drawing a raffle ticket from a hat and not replacing it will affect the outcome of drawing a second ticket. Because if you took out 1 ticket, you've got less tickets in total, so the probability of the next ticket will change. These 2 events are therefore considered to be dependent. So that's an example of an event without replacement. However, if you did replace the first raffle ticket in the hat before you drew the second ticket, then the events are suddenly now independent, because the probability of the second event occurring wasn't affected by the outcome of the first event, the first ticket being drawn. So that's very important. So the first one, where it's dependent, is an example of an event with replacement, and the independent one, sorry, other way around, this one is without replacement, the dependent one. The independent one is with replacement of the ticket. Remember this, you calculate the probability of A and B, which is the intersection of A and B, meaning like this little part here. So you calculate the probability of A and B by multiplying the probabilities together. So the probability of A and B, which is the intersect, equals the probability of the intercept. I might also want to write here, of A and B. which equals the probability of A multiplied by the probability of B. So in a lot of your exercises in this section, you'll be multiplying probabilities together. Similarly, you calculate the probability of A or B. So notice the one above has A and B here, and this one is A or B. A or B we consider to be the union. I'm just kind of doing that properly. So I'll just color it in. So the union meaning all of it, not the intersection, but the union. So similarly, you calculate the probability of A or B, which is the union of A and B, by adding the probabilities together. So we have an add in here. And this little summary here will be very useful kind of throughout this whole 3 lessons on probability. So you might want to kind of highlight, put a little highlight box around this or something like that. So when you look back through your notes, you'll see that this was important. Now let's try to apply some of that. So we've got the coin and the die are tossed and rolled simultaneously. Are the 2 events independent or dependent? So try to think, the outcome of flipping a coin, will that affect the outcome of rolling a dice at all? No, not at all. So you would say the 2 events are independent. Independent. If you want, for your notes, you can write reason, for example, i.e. the outcome of rolling a die does not affect the outcome of tossing the coin. So therefore they're independent events. Determine the probability of a tail, here's a key word, and a 4. So you can think of that probability of tail and a 4. Think of like the intersect. The intersect looks like an A, so tail and a 4. So it's a tail, probability of tail intersect 4. So what's the probability of getting a tail when you flip a coin? It's just 1 in 2. And because it's the intersect, we multiply by the probability of getting a 4. Probability of getting a 4 on a dice is just 1 in 6. And remember, when you multiply fractions, you multiply the numerators. 1 times 1 is 1. Then multiply the denominators. 2 times 6 is 12. Can you simplify that? No. So it's answered. Determine the probability of a tail and an even number. So it's and again, so it's a probability of a tail intersect an even number. If you want, you can write it like that. Tail and an even number. So probability of a tail, you know already, that's just 1 in 2. And because it's the intersect, it's probability of and. We multiply. Even numbers, there's 3 even numbers on a dice, 2, 4 and 6. So it's a 3 and 6. You might have said 1 and 2, that's also okay. 3 and 6 chance of getting an even. And multiply the numerators, you get 3. Multiply the denominators, you get 12. But you can simplify that fraction. The top and bottom can be divided by 3. Sorry, by yeah, they can be divided by 3, sorry, which gives you 1 in 4. Now determine the probability of getting a head on the coin and a number greater than 4. So by number greater than 4, we mean, for example, a 5 or a 6. So let's go set that one up. Probability of head, and it's got the word and. So intersect number greater than 4. If you want to do that. Just being lazy there. You could have written out the words greater than 4. So probability of the result of tossing a coin being a head is 1 in 2 multiplied by probability of a number greater than 4. So you can see there's just 2 of them, 2 out of 6. 1 times 2 is 2, 2 times 6 is 12, which simplifies to 1/6. So again, notice I'm simplifying all my fractions. Let's move down to a different example this time. So I've got a box contains 4 red and 2 yellow tickets. So a total equals 6 tickets in total. 2 tickets are randomly selected from the box, 1 by 1, without replacement. That's really important, without replacement. So after they've taken the first ticket out, there's only 5 tickets left to choose from. Find the probability that both are red. So that's like saying a red and a red. So probability of a red and a red means probability of a red intersect red, which means you multiply the two probabilities together. So there's 4 red to begin with, so there's a 4 in 6 chance because there's 6 in total. But because you're not replacing, once you take that first red one out, there'll only be how many tickets in total left? There'll only be 5 tickets in total left because it's without replacement. So you take that first red ticket out, and how many reds would be left? If you've already taken a red out in the first go, there's only going to be 3 reds left out of the 4 the second go. So therefore, then you just multiply the numerators and the denominators. 4 times 3 is 12, 6 times 5 is 30. Top and bottom are divisible by 6, which will give you 2 over 5. So that's question A. Let's do question B over here. So here they're saying the first is red and the second is yellow. So that's an N there as well. So it's probability that the first one is red and the second one is yellow. So probability of the first one being red, of course, is still just 4 over 6, and it's an and, so we're multiplying. Probability of a yellow, it's without replacement, so the denominator's gone down to 5 because you took a ticket out and didn't replace it. The first time around you took out a red, so how many yellow tickets would be left? There'll still just be 2 yellow tickets left. And then work out the answer. 4 times 2 is 8, 6 times 5 is 30. Top and bottom are divisible by 2, which gives you 4 over 15. Chance that the first ticket is red and the second ticket is yellow. Let's move on to the next one. A hat contains tickets with the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I forget, includes 20. 20 printed on them. If 3 tickets are drawn from the hat without replacement, again without replacement this time, so the denominator is going to be decreasing by 1 each time, determine the probability that they are all prime numbers. So this is a fair bit more working out, well, to some extent. So by prime numbers, what do we mean? E.g., numbers 1 to 20, what are the primes? 2, 3, 5, 7, 11, 13, 17, 19. That's what we mean. How many prime numbers are there? There are 8 of them in total. So it was worth working that out first. So probability of getting a prime to begin with, and another prime, and another prime. I might just do that, P, D, P. Probability of prime, and a prime, and a prime. You can use the intersect sign if you want. So how many are there to begin with? There's 8 to begin with, out of a total of 20 tickets, because we've got numbers from 1 to 20 on the tickets. And it's without replacement, don't forget that. So how many primes would be left after that? There'd be only 7, and a total of 19 tickets when you take out the set. So after you've taken out the second ticket, how many primes would be left if the first 2 were already prime? There'd only be 6 primes left, and a total of 18 tickets left in the hat. And now what you have to do is multiply all the numerators, multiply all the denominators. So we've got, when you multiply the numerators, you get 3, 3, 6. When you multiply the denominators, you should get 6, 8, 4, 0. And that can simplify. You can simplify it yourself, or your calculator can do it too, to 14 over 285. Remember that was without replacement. Here we've got a litter of kittens. Contains 6 ginger, 2 white, and 4 tabby cats. So how many in total is that? 6 plus 2 plus 4. Total equals 12 little kittens. So 3 cats, meaning kittens basically, are randomly selected as pets for one family. So find the probability that all 3 cats are ginger. So like a ginger and a ginger and a ginger. So I'll just write that quickly here because I'm running out of space. Probability GGG. To be honest, if you want to, you can just write it really quickly like this. GGG. Probability of ginger. So to begin with, there was 6 ginger. So there's 6 out of 12 that are ginger. Oops, I don't know where the comma. 6 out of 12 and it's an and, a ginger and a ginger and a ginger. So if you, first one selected was ginger, there's a 5 in 11 chance of getting another ginger, because there's 11 in total and only 5 gingers left. And the fourth ginger, therefore, makes sense, is 4 out of 10. And again, just multiply the numerators, multiply the denominators. You get 120 over 1320. You can simplify it yourself in your calculator as well. That gives you 1 out of 11 chance of getting 3 ginger cats. So interestingly, probability all are white. So this is tricky because it's asking 3 cats and 2 are white, but to show working out, you can still go probability white, white, white. I'll do it down here to save a bit of space. Equals, there's a 2 in 12 chance that the first one's white, and then because you've already selected a white cat, there's 1 cat left out of 11 cats left in the litter. Oops, I don't know why I'm doing commas again. So 2 in 12 to begin with, multiplied by 1 in 11, multiplied by 0 white cats in 10. If you multiply the numerators and the denominators in this case, you'll get 0 over 1320, which of course is just equal to 0. So there's a 0 chance that all cats will be white. It does make sense, because if you've only got 2 cats, you can't get 3 cats that are all white, because there's only 2 white ones in the litter. This next one takes quite a bit of work, so write small is what I'd recommend. What's the probability of one of each type is selected? So it's like saying probability of ginger, white tabby. The order is kind of important. Plus probability, white, ginger, tabby, plus the probability that the first one's tabby, second one's ginger, next one's white, plus the probability of tabby, then white, then ginger, plus the probability of ginger, tabby, white, and then look through, is there any other combinations we've missed? Yep, we've missed one combination, probability that the first one's white, second one's tabby, and the third one's ginger. So there's 6 combinations in total. We've got to work these all out, but it turns out they're all quite similar. So first one, ginger, white tabby, is 6 in 12 times 2 out of 11 times 4 out of 10. Because there's still, even though you've taken a ginger cat to begin with, there's still 2 white cats and 4 tabby cats. But the denominator is dropping, you'll notice. Plus, to the next one, 2 out of 12 times 6 out of 11 times 4 out of 10. Plus this combination, which is 4 out of 12 times 6 out of 11 times 2 out of 10, plus the fourth combination, tabby, white, ginger, which is 4 out of 12 times 2 out of 11 times 6 out of 10, plus fifth combination, ginger and tabby, white, so that's 6 out of 12 times 4 out of 11 times 2 out of 10, plus the last combination, which is white, tabby, ginger, which is 2 out of 12 times 4 out of 11 times 6 out of 10. Notice for all of those, the numerator will be the same number. 12 times 11 times 10, you worked it out before, it's just 1320. So you can write your answer here on the side if you don't have space, or next to the kittens. I'll just write it down below. So that in total equals, so 1320 on the bottom. And you'll notice that in this particular case, the numerator is always going to be the same. It's always going to be 6 times 12 times 4. Let's see, how does undo that? 6 times 12 times, sorry, 6 times 2 times 4. So 6 times 2 times 4 equals, just one second, I've just got to fix something. Here we are, back again. So yeah, when you do 6 times 2, that's 12. 12 times 4 is 48. And in a way you're adding it to another one, which is 48 numerator, 48 numerator, 48 numerator, 48, 48, and so on. So if you wanted to do that quickly, you could just do 48 multiplied by 6, which gives you 288. and that simplifies to, let's see, 12 over 55. If you were doing it as a decimal, it would be 0.218, and the 1/8 part is recurring, so put a line over the 1/8, and so on. And that's the end of that lesson. That last one was a particularly tricky one because they didn't specify an order. If they said a ginger and then for the first cat, a white for the second cat, and a tabby for the third cat, then it's easy. It's just the first one that is in blue up here. Would have been that particular one only. But because they didn't specify any particular order, I had to work out all the combinations first. So fortunately, hopefully in a lot of your questions in the exercises, they do specify an order. And that's the end of the first lesson on probabilities.